And welcome, students, as we dive into our big unit on data structures. Let's go ahead and start with our first one that we're going to look at, which is that of linked lists. And to kind of get us started here, we're going to just kind of do a quick introduction onto the concept of nodes and onto that of a linked list. So before we actually fully get started with the lesson, let's just talk really quickly about what a node and a link is. So a linked data structure consists pretty much of capsules of data, or what's known as nodes, which are connected via what are known as links. Well, these links can be viewed as arrows and thought of as one-way passages from one node to the next. So the simplest kind of linked data structure consists of a single chain of nodes, each connected by the next in the link. And this is known as a linked list. So it's just like you can think of like a chain link fence. In other words, it's one link to the next link to the next link to the next link. It's just one solid line in this chain. So this is kind of what we're going to be looking at here for our first few sections here, is that of a linked list. A sample linked list is kind of like what you see here. We have our head of the link, and of course then we'll see it's like roles 10, jams 3, milk 1, T2, and then an end marker. Now this right here may seem a little abstract right now, but we haven't really talked about what all these different components mean. Only data structures we kind of have in mind up to this point have been arrays and array list, but they aren't necessarily what we want to be able to use. So in our list here, you'll notice that the nodes are represented by boxes that can each hold two types of data. We can hold a string and an integer, such as a shopping list in this case. The links, therefore, are depicted as arrows, which reflect the fact that your code must traverse the linked list in one direction without backing up. In other words, once it starts going down that list, it can't go back to it. All right, it has to go all the way through it. And pretty much, and if you want to retraverse it, then you can go back to start. But you have to go all the way through the list. There's not like you can go 1, 2, 3, back to 1. You have to go 1, 2, 3, 4, 5, all the way to the end of the list. And then that's the only direction you can move. So there is, in this case, a first node, a second node, and so on, all the way up until we reach our last node. There's not a finite amount of nodes that have to comprise. Like, we're not going to say, oh, the max size on a linked list is 10. All right, it's really more of a memory limit here. So you don't have to say, oh, I'm going to have 100 linked list items. It's going to be a big list. Yes, it could be a big list, but for our purposes, don't worry about the size of this when we first get started. Now, the first node that we're going to be looking at, of course, is what is known as the head node. This is the first node in your list. This is your position 0. All right, so now that we've kind of established a little bit of the terminology, let's actually get started with the lesson for today. All that information I've kind of talked about up to this point is kind of vague. All right, it's not necessarily clear on how this is implemented in terms of programming, but it does provide a general picture of what is going on inside the linked list itself. Now, it becomes a little bit more concrete for us to understand when we actually create a linked list in some programming language. And naturally, because we've been using Java, we're going to take this from the idea that nodes are realized as objects of a node class. So the data in the node is stored, therefore, via instance variables. The links are then realized as references. And if you recall, reference is simply just a memory address. So where is that location in memory? And then a reference is what is stored in a variable of a class type. So the link is realized as an instance variable of the type of the node class itself. Now in Java, a node in a linked list is connected to the next node by having an instance variable of the node type contain a reference, or a memory address, of where in memory the next node is stored. So Java actually comes with a linked list library as part of the java.util package. Now it makes sense to use this library class because it's well designed and well tested and will save you a lot of work. However, even though there's a linked list built in, it's not really going to teach us how to implement the linked list structure itself in Java. So to do that, we actually need to see more of an implementation of a simple linked list structure first, such as a linked list. So in order to kind of get a good understanding of how this thing is done in Java, we're actually going to construct our own simplified example of a linked list first before we get into using the one that's built into the Java libraries. So a linked list is simply, again, just a linked data structure consisting of a single chain of nodes, each connected by the next by a link. This is the simplest kind of linked data structure, but it is nevertheless widely used because sometimes simple is good. All right, so let's look at our example here of that simple linked list that I've been talking about. Recall our diagram that we had back in the I think it was the second slide of a linked list. In the display, the nodes are the boxes, and in our Java code, the node would therefore be an object of some node class. So this would be class node 1 in your class materials. Now each node has a place, or sometimes places, for data and a place to hold a link in another node. The links are shown as arrows that point to the node that they quote-unquote link to. In Java, the links will therefore be implemented as references to a node stored in an instance variable of the node type. The node1 class, in our case, is defined by specifying, among other things, an instance variable of type node1 that is named link. This allows each node to store a reference to another node of the same type. There is a kind of circularity in such definitions, but in Java, that's perfectly okay. One way to kind of see that this definition is not logically consistent is that we can draw pictures or even physical models of our linked nodes. And that's a lot of times why we will use like the diagrams that we have still, like back in the first slide, of the linked list structure. All right. Now, before I continue on, I just want to pop over to Eclipse real quick and just show you the node1 class. Of course, again, this is in your class materials. So here, of course, we have our private instance variables. I have a string, an int, and I have a node1. So you can see node1 also contains a node1. All right, so that's why we talk about it has that circularity right there. Then, of course, we have our constructor, public node1, link is null, item is null, count is 0. All right, and the reason why these are set to null because remember, string and node1 are classes. All right. Then we have one that actually takes in parameters. Here's our constructor with parameters. So string new item and new count, node 1 link value. All right. So you'll see that set data is a call that sets new item and new count. Link, of course, is equal to link value. And if we look at that, it means that this is going to call the set data method, which is right here, which passes in a string and an int. String and int, of course, item is new item, count is new count. And then, of course, from there, we also have other options such as set link, which simply sets the node 1 to a new link. We have string get item, which returns the item, get count returns count, and get link, which returns the link. So that first node, or the starting node in a linked list, if you recall, is called a head node. If you start at the head node, you can traverse the entire linked list, traversing and visiting each node exactly once. And as we will see kind of in a moment here, Java says to your code, hey, follow the link arrows. So in our diagram, the box that was labeled head, if you recall, is actually not the head node. In fact, it's not even a node. The box that was labeled head is a variable of type node1 that contains a reference to the first node in the linked list. That is a reference to the head node. That's why it was placed off to the side with the arrow pointing to everything else that was in the kind of the same column. So it is actually just the variable, not the actual list itself. The function of the variable head is that it allows your code to find that first or the head node, because we have to know, well, where's that location at? Now, the variable head is declared in a pretty obvious way. Node 1, head. That's it. Nothing too complicated. Now, in Java, a linked list is simply just an object that, in some sense, contains all the nodes of the linked list. Linked list 1, which is our first simple linked list, contains a definition of a linked list class for a linked list such as the one in our diagram. You'll notice also that a linked list object does not directly contain all the nodes in a linked list. It contains only the instance variable's head that contains a reference to the first or head node. However, every node can be reached from this first or head node. And the link instance variable of the first and every node 1 in the linked list contains a reference to the next node 1 in the linked list. Thus, the arrows shown in the diagram are realized therefore as references within Java. Now, each node object of a linked list contains in its link instance variable a reference to another object of the class node 1, and this other object contains a reference to another object of the class node 1, and so on and so forth until pretty much the end of the linked list. Thus, a linked list object indirectly at least will contain all the nodes within the node list. All right. So before I move on to that, I'm going to show you linked list 1 just so you can see how that looks. So here's linked list 1. You can see, of course, here's our private node 1 head. Here is my public linked list construct where the head is saying to null. And then, of course, right here, this method adds a node to the start of the list with the specified data. The added node will then be the first node in the list. So this is our add to start method here. And then, of course, right here, this removes the head node and returns true if it contains at least one node. It's false if the list is empty because, well, if the list is empty, you can't really do anything with it. Then, of course, down here, we have some other methods. We have one that returns the number of nodes in the list. So if you want to know how big your list is in terms of node size, that's a quick and easy way to do that. Here's simply just a contains method that simply just says, hey, it contains a string. This right here finds the first node containing the target item. So this is just going to find like a string with that value. And then this one right here, output list, obviously is just outputting the item. So it says position.getItem, so it's calling that getItem, and then position.getCount. So it's calling those methods right there. All right, let's move back to our presentation here. All right, so when we are dealing with a linked list, your code needs to be able to get to that first head node. And you need some way to detect when the last node is reached. To get your code to the first node, we use a variable type node1 that always contains a reference to the first node. In linked list 1, as we saw, the variable with a reference to the first node is simply just named head. From that first or head node, our code then can follow the links all the way through the linked list. But ultimately, how does your code know when it is at the last node within the linked list? Well, let's take a look at another diagram here to kind of help us digest this. In Java, we indicate the end of a linked list by setting the link instance variable of the last node in the linked list to null, as shown below. So you can see here, if we follow, we've got our head variable pointing to roles 10, and then of course we have position pointing to jam3. This is the reference, is position.getLink, and then of course milk1, t2, and you'll notice this right here, when it's at the last node, position.getLink equals null. All right, so it changes right here to null. And that is the key differential here, is that instead of pointing to another memory reference, it's going to instead point to null. This is the way that our code can test whether a node is at the last node in the linked list by simply just testing whether its link instance variable is null. All right, so if it contains null, that's the end of the list. Congratulations. Remember that you can check for link being equal to null by using equals equals, and not by using any equals method. So you're not going to do like link dot equals null. That's not how it works. It's a state. So you use link position.getLink, and then you notice that this right here shows two parents. So this returns a value, and we want to see if that equals null. All right, that's how we check that. Also, remember to use null in order to indicate an empty linked list. So you'll notice that when we initialize a lot of stuff, we initialize it to null, because null, of course, means that there's no value. So if we have a linked list created, but we don't put anything in it, that's why everything's still initialized to null, because we don't actually want to give it any pointing values. So the head instance variable contains a reference to the first node in the linked list, or it contains null if the linked list is empty. That is, if the linked list contains no nodes. Just as I mentioned, if you look back at our code, we'll say like head equals null. The only constructor sets this head instance variable to null, indicating that a newly created linked list is empty. That's pretty much just what I've been pointing out here the last few lines. If we want to actually get into, now let's say, traversing that linked list. Okay, so we made the list. What can we do with it? So let's just try going through it. Before we get into discussing, though, how we can add and remove those things from the list, we have to first, of course, say, hey, we have a list, we created it. How do we want to get values from it, for example? All right, we want to write out the contents of all the nodes to the screen. Well, we can do this with the method output list, which by the way I've reproduced here. Node 1 position equals head, while position does not equal null. This is null.println, position.getItem plus space, position.getCount, position equals position.getLength. And that's a very simple code. It just outputs what we have in the list. Now the method uses a local variable named position that contains a reference to one node. The variable position starts out with the same reference as the head instance variable, so it starts out positioned at the first node. The position variable then has its position removed from one node to the next with the assignment position equals position.getLink. So that's all you got. Position equals position.link. That's how it updates. So when we actually look at traversing the linked list, here's our diagram again. All right, we can see how this is therefore illustrated within this diagram. So to see that the assignment moves the position variable to the next node, note that the position variable contains a reference to the node pointed by the position arrow in the diagram. So right here is position, right here. So position is a name for that node, and position.link is a name for the link in the next node. The value of link is produced with the accessor method getLink. Therefore, reference to the next node in the linked list is position.getLink. So of course, you can see right here, we have position.getLink. All right, and of course, down here, when we do this one, position.link is equal to null because it's the last node. All right, we can move the position variable by giving the value of position.getLink. That's why we say position equals position.getLink. So like this one right here, we say position equals position.getLink, moves it down. Then when this one runs, it's going to move to here. And when it runs to here, oh, this is null. That's the end of the list. Now the method output list continues to move along the position variable down the linked list and outputs data in each node as it goes along. Kind of as I just shown you a second ago with the list. So it's going to go from one to the next, to the next, to the next, until it reaches the end. Now when the position reaches last node, outputs the data in that node and then again executes position equals position.getLink. Now if we looked at that diagram, you'll notice that when the position leaves the last node, its value is set to null because we have the getLink equals null. At this point, we want to stop the loop, so we iterate the loop while position does not equal null. So that's very important that we make sure we say position does not equal null, because as soon as it's null, what's it going to do? It's going to exit that loop. Now, a similar technique is used to traverse the linked list in the methods size and find. So if you look at how we use size and find, you'll see that they run very similar. All right, now that's enough about moving along it. Let's actually add stuff to it. So we actually want to add stuff to a list. So let's consider how the method add_to_start adds a node to the start of the linked list so that the new node becomes the first node in the list. It does this with a single statement, head equals new node 1, item name, comma, item count, comma, head. The new node is created with new node 1, item name, item count, head, which returns a reference to this new node. The assignment statement then sets the variable head equal to a reference to this new node, making the new node the first node in the linked list. So to link this new node to the rest of the list, we need to only set the link instance variable of the new node equal to a reference of the old first node. But we've kind of already done that. Head used to point to the old first node. So if we use the name head on the right-hand side of the assignment operator, head will denote a reference to the old first node. So that's the reason why we put it in here. So you see the head is kept here as part of the constructor. So in that assignment, you'll notice that the new node is produced by new node 1, item name, comma, item count, comma, head, which points to the old first node, which is just what we wanted. So we notice here's the original head. All right. So this is the new node beer, comma, 6, comma, head. All right. And new node 1 creates the node and positions here. So here's where you have the pretty much the head, which was pointing here before, is now being moved to point here. And if I were to add another node in, let's say I have one for pizza, I could put one here, and this head reference, instead of pointing here, would then move to point to the new one because it puts it at the top of the list. All right, and as I mentioned, this is already illustrated. So that's adding. Let's look at removing. All right, later we'll discuss adding nodes to other places within the linked list as we get further into the chapter, but the easiest way is to place a node at the start. All right, easiest way to do it. There are other ways, but the easiest, again, is just putting it right at the start. Similarly, the easiest place to delete or remove a node, therefore, is at the start of the list. If it's easy to put it at the front, it's also easiest to take it off the front. The method delete head node removes the first node from the linked list and leaves the head variable pointing to, that is containing the reference to, the old second node, which is now the first node in the linked list. This is done with the following assignment, head equals head.getLink. Boom. You notice it's very similar to position equals position.getLink. So by doing that, it moves that head variable kind of just like you would see the position one moving down a reference point. The same thing is happening here. All right, automatic garbage collection. All right, and this is very important concept to know how Java handles memory. So this, of course, you'll see remove the first node from the linked list and leaves the linked list one node shorter. All right, so before it was like, let's just say at memory position 3000, and we moved it down one, so now it's at 3001. Hey, great, it's one shorter. But what happened to that node that was at position 3000? All right, what happened to it? Is it just stuck hanging out in memory until like you shut your computer down? Like what happens? Well, at some point when your program's running, Java is going to automatically collect that node that was at position 3000, all the data and stuff that was stored there, along with any other nodes. So let's just say I have an unused one, let's say at 3100, and an unused one, like let's say 3105, maybe one at 30,086, and it's going to say, hey, these are no longer accessible by the list. So I'm just going to recycle the memory that is being occupied by them. I'm going to free it up. This is what's known as automatic garbage collection. Now, is it Java's the best way of handling it? There's some debate about that, but Java's like, hey, you got the stuff hanging out here. It's not being used. Let's clean that up. Now, the linked list demo one that you'll see in your notes contains a very simple program that demonstrates how some of the methods in our class linked list one behaved. So before I kind of get into that demo, quick, I just want to mention to you some privacy leaks here, because obviously as we start dealing with memory being allocated, reallocated, collected with the garbage collector, there are some potential things that can go on here. All right, so if we look at the method getLink back in the class node1, it returns a value of type node1. That is, it returns a reference to node1. Now, in program 1, we said that if a method such as getLink returns a reference to an instance variable of a mutable class type, then the private restriction on the instance variable can be easily defeated, because getting a reference to an object may allow a programmer to change the private instance variable of the object. Therefore, there are several ways in order to fix this. The most straightforward, which is to make the class node1 a private inner class in the method node1, which we'll actually look at how to do that in the next lesson. So by making it inner class, hey, we're that much better off in terms of security. All right. Additionally, there is no danger of a privacy leak with the class node1 when it is being used in the class definition for linked list 1. So technically, the way we have it structured right now, we're golden. However, there's no way to guarantee that the class node1 will be used only in this way. So if I were to make a different class and structure it differently, well, unless there's some precaution taken, such as the aforementioned making it a private inner class, you're going to run into some issues. Now, an alternate solution that you can do is to place both of the classes node1 and linked1 into a package, and then change the private instance variable restriction to that of a package restriction, so they're only valid within that package. Now, you'll note that this privacy problem can arise pretty much in any situation in which a method returns a reference to a private instance variable of a class type. So that's kind of the drawback of having to do this. The method getItem of the class node1 comes very close to having this problem. I mean, if we're using it just how we're implementing it in the notes, you're good. But if we start doing it in other ways, well, then we could start running into some issues. In this case, the method getItem causes no privacy leak, but only because the class string is not a mutable class, that it has no method that allows you to change the value of the string without changing the reference. If instead of storing type data in our list, we had stored data of some mutable class type, then defining an accessor method similar to getItem would probably produce a privacy leak. So just good things to keep in mind here as you're developing your code. All right, and now let's go ahead and pop back to Eclipse here, and you can see here's our demo. So let's actually see how this linked list works. So I have a linked list that I've created. I'm going to add to it these 3 items here. Then I'm going to output the size of it. I'm going to output the list, whether a cantaloupe is on or not. I'm going to delete it off, output whether it's on the list or not. Delete the head node, print out the start of the list, print out list, and then print out end of list. So here we go. So we run this. All right, you'll see that the list has 3 nodes, so that's the size. Then, of course, we output the list. So here's cantaloupe 3, bananas 2, apples 1. Then, of course, I came through here and said, hey, does this contain cantaloupe? Yes, it does. I deleted the head node. Cantaloupe is not on the list anymore, so it says it's not on the list. Then I'm going to delete the head node, and you notice that this empty loop body just pretty much runs this until pretty much it's done. So then you'll see start of end list, empty, and end of list. All right. A pretty simple example here for you to look at when you're starting to get into how to work with a linked list. But I know it's a little bit longer than some of our other notes that we've looked at, but hey, we're getting into the good stuff now. Linked list is one of those first big data structures that we can use to really help us make some pretty awesome programs. All right, with that being said, I will see you the next time.